There we go. Okay, welcome everyone to today's live stream. It's a live science session, and today we're joined by Nick and Mads. I'm James, and we're going to be talking about some quantum paradoxes. And that's the clickbait title, but no, really, we're going to be looking at the quantum framework that's been developed and how to start actually programmatically constructing some of these quantum circuits in a notebook, which is pretty cool. And hopefully we could get to actually computationally ponder some of these paradoxes in code, and might reveal how these paradoxes are actually not paradoxes. Maybe not. Maybe it'll just make us more confused. But yeah, we'll let Nick guide the exploration for today.
Yeah. So I have prepared some of the notebooks. We've been exploring a bunch of those so-called paradoxes recently, like starting from basics, looking at the double slit and like improving it, to the delayed choice experiments, right? And even like looked at more questions about Wigner friends and all of that. And like in the middle of that, I also like looked into more basic Bell inequalities and looked back to my CHSH circuits and how you can also like think about them again. There's some, I kind of developed some new narratives how to talk about this kind of problems.
Very cool.
So let me just start sharing.
And Carlos is joining us as well. I just did the intro. Okay. And we are streaming. Okay, we can see your screen. Looks good. What's the zoom on that?
100. Let's increase it.
Perfect.
So that's the first notebook I guess we should go through. And it starts with just like the basic quantum theory about double slit and how you would implement it in a circuit in two different ways, essentially. It's like, because usually when you Google it, the usual setup people do when they try to model the double slit experiment and all the derivatives of it using the optical table and optics, it's like you're gonna find like pictures like this, right? So it's not usually described using double slits directly, and the pattern on the screen, if you want to make some circuit without like complicated screens involved, you have to do some kind of interference and just some finite counters, detectors of photons, if you want to explore this kind of problem using.
Oh. Nick, okay. So one thing, like, just to give, like, the audience a sort of like, general intro, like, as you may know, from the very beginning of, quantum theory kind of like, puzzled many scientists, and they had a very hard time, like, understanding of that. And what we are trying to do here is basically providing, a framework for users, for scientists to explore these ideas. Like, this is what we usually refer to as, computational experiment. So like, that's what we are trying to achieve here. And we may use some terminology, some terms that kind of, they may imply that, like, oh, in quantum, there are some mysteries, there are some paradoxes, etc. But keep in mind, like, we are scientists. Like, the main goal of a scientist is demystifying the nature. So excuse our, like, bad terminology. So we are not gonna talk about any mystery or any spooky things. It's just pure, scientific approach to some very difficult foundational problem of quantum theory. I think, like, part of that, like, it's in a sense, we can go back to founding father of quantum theory. Like, I really like the way that Niels Bohr described the whole problem. In classical world, the way that we understand the nature is basically, using classical concepts. Okay, like, that's how we understand nature. All of our measuring devices, like, at the end of the day, like, it seems like, we understand them, in a classical way. When it comes to the world of quantum, it seems there are some serious limitation on applying those, clear ideas to the quantum world. So it is as if, like, there is a boundary, there is a region, like, beyond which, like, those conceptions are not applicable anymore. And from the very beginning, like, many scientists, they were struggling to understand, okay, where is that boundary? Like, where we can say is quantum, where is, like, classical. And this is, some people, they usually refer to it as, like, measurement problem. This is, some other people, they call it like collapse of the wave function, like, state reduction, like, it has many different names. But at the end of the day, it's like, if you say the whole universe and everything is, unitary and Schrodinger evolution, so you will have a very hard time understanding of, like, your observations, like, what happens. And then it has many different scenarios. We have Schrodinger cat, and then we have Wigner friend, like, you can make it even more dramatic. Like, we have one level of drama with Schrodinger cat, and then, Wigner bring it to the next level now. Like, it's the conscious of, like, observer that may play. This is basically, like, a quick summary of everything. And interestingly enough, like, the whole idea of why quantum is interesting and why it is useful for some computation is because of those unique features. We have superposition, we have entanglement, and these are the things that helps us to do, like, novel things. And, today, like, Nick, go, hand it over to you. Like, at the center of, like, some of those conversations, there are some famous examples. One of them is double slit experiment. Let's see how we can understand double slit experiments in Wolfram quantum framework.
Yeah. Well, there are multiple approaches to that. It's like the most common way of doing it, like, and you'll find almost everyone's gonna do it in this way, is just directly model this particular splitting and interference pattern of your multiple beams, like one coming for one slit, another one coming for another. Usually you model it by just a superposition, right? So if you start with a zero state and interpret it as like your initial laser beam located in a single position, turning it into superposition means you turn it into basically into different state that now interpreted differently, so that zero now is interpreted as a laser going, beam going to the left slit, and one means going for the right slit. So you model the path directly using the superposition, right? So that now then you apply some, which you can do by applying Hadamard gate. So that's what you see here as a first gate in the circuit. That means when you apply your Hadamard gate to the zero state, you get the same +1, the superposition of left and right path, right? The next piece in this circuit is, in order to introduce the interference, you have to introduce some phase difference between those two paths, right? And it's usually just done by the phase operator, which concretely just applies some shift to the to the one state, which you can interpret as one of the holes that your beam is going through. So just one coefficient before the one is gonna appear when you apply this phase gate, right? And then how would you model the collection or the interference effect? Then basically the reverse of that first splitting that you did with the Hadamard gate, you just apply the Hadamard gate again, and basically that introduces the interference. So you apply this guy again to this shifted state, and that's basically your resulting state that you're gonna observe when you measure it. Then you measure it, and depending on which what was the phase shift was, which you model just with a single parameter here, which is like theta, which is just going to model the direction of this point on the screen. You can basically plot it or directly measure it. You get some distribution, which is going to be like going to look like a sine curve, which is like the usual interference pattern if you literally just plot it through 0 to 6 pi or something, right? You get some curve that shows the density of points on the screen. So that's the interference pattern. So the paradoxes arise in that particular experiment is when you try to measure which actual hole the photon goes through. And that's usually, you can model it by correlating your path to some additional system. So you literally, on the circuit diagram, you introduce the second system, that's this second measurement device that you're going to apply before the photon goes through the hole or after, in order to actually observe it. And you model the correlation between those systems with the photon and this measurement device by just some controlled node. Basically, you condition whether you measure 0 or 1 based on the photon that was already chose the direction it's going through, right? And you measure both of them. And as soon as you do this, nothing else has changed. You compute the probabilities of this particular photon, how it depends on theta, and you get no dependence on theta. Basically, it's just a flat, uniform distribution of points on the screen. So you see no interference. So that's how you interpret it, how you did interpret this kind of setup.
So basically, like, this is in a sense like, the famous, complementarity principle. When you record the path information anywhere, so you are basically dealing with particle nature of like, your system. And when it's particle, as you see those probabilities, like, they are classical distribution. You don't see the interference pattern. But when that information is not there, or when you don't look at it, like, you end up with wave behavior, which is the interference that, Nick showed initially. Yeah. Now there are like, lots of different scenarios that like, people, they can play around, such as like, erasing that information and see what happens if you do that.
Yeah. Well, I was also going to comment on the wavy nature, particle versus waves and all that. It's like when you have this setup as a diagram, you can basically just go through all the gates one by one and see what's happening in the intermediate state, what state you have. You can interpret it probabilistically. Your measurement is also can be put at some kind of decoherence. It's just an additional map that acts on a state or probability distribution. It's like just to bring the idea that nothing wavy in particular has to happen in order to explain the same effect, right?
That's my question, is this concept of the wave-particle duality, is the waviness just a nice analogy, or is there evidence that it's an actual wave? Is it just a way for people to describe it visually and for people to easily understand?
You can think of it as a very nice analogy because mathematically it's very natural to describe it this way, turns out. That's why complex numbers play such a big part in this formalism, right? So it behaves like waves, but it doesn't have to be explained this way.
Got it.
Yeah, I can reinforce the point maybe by saying that in some sense the wave duality, the particle wave duality of quantum mechanics doesn't really pose a paradox. It only poses a paradox when you, for some reason, decide to have the mentality of a physicist from the late 19th century or early 20th century. In some sense, when you accept that nature is what it is, and you can have access to nature with this particular experiment, you realize that the interference of electrons through a double slit is part of nature. Then there's no paradox in place, right? Then there's no ambiguity. It's just you wanted to think that electrons are waves or particles. You were just wrong to assume that they were one or the other, right? They behave exactly in this way informationally, and that's what we observe. And this is a real experiment, right? You go to the lab. I've done it myself. In first year physics, I went to the lab. You're like, close one slit, you see a perfectly nice Gaussian distribution. You open the second one, and then you see a pattern of scatter-like lines. So there's no, I mean, it was just the intuition of physicists thinking, oh wait, the electrons are coming out, and I can count the blips in my detector. Therefore, they must be like the cannonballs that Newton was thinking about in the 17th century, right? So in some sense, like historically, these are paradoxes in a very historical sense. But once you take all the kind of evidence that we've gathered, they don't really behave paradoxically in any sense, right? It's very counterintuitive. I'm not going to dismiss the fact that it's something odd is going on for a human intuition, but in a sense, from a purely physics or scientist point of view, there's nothing like mysterious or spooky going on, I would say, personally.
Basically, waves are very natural to consider when you do the math. But I can argue even for the particle case. I have a very very weird explanations how a particle would work in such scenario when you try to explain everything without waviness, but purely with probabilities. We can maybe mention it later. But now we can continue like this, describing the double slit one. So the erasure Mats mentioned, that's the procedure people usually consider when, from this explanation, what actually destroys the interference. It's when you try to measure which path the photon chose, so you know the which way information. So in a way, you can restore your interference by somehow erasing this information, right? And in the circuit, this erasure basically can happen by this literal effect applying to that particular information. You erase it by applying this effect, or it's like a dual to the superposition. So you don't know, this correlation can bring your measurement device either to 1 or to 0 or 1. Basically, you know which path the photon chose, which either left or right. But erasure means you kind of sandwiching it between completely like just superposition state instead. That's how it is erased in practice. You don't measure it or do anything like that. You quantum mechanically apply this thing, which can be, I guess, in practice interpreted as, I don't even know.
Adding a filter. It's like adding a filter, you have a very specific filter that passes, for example, think about that zero, think about it as, polarization. And then, you put a filter that passes only a specific polarization. Of course, the price that for erasing is you are going to lose, I don't know, what's the right terminology? It's like you are looking into half of original statistics. So that's the way that that we should understand it, because instead of plus, people, they can also put minus. So it's the other half. And and if we look at both of them at the same time, the result would be very interesting, because people, they would see the complementarity of those two things at the same time.
Yeah, you can even model it by additional angle.
Yep.
Oh, where did the dagger disappeared? All right, and you maybe do the 0 instead. So basically, the amount of erasure. Now you model the amount of erasure depending on this angle. If it's 0, I guess it's still gonna be, there's still gonna be an interference, right?
If it's 0, there is no interference, and then as you get closer to plus, you would get the maximum interference again.
Oh,
yes. So let's try to do it. So this circuit is now parametric. It takes 2 parameters. Right? I just do the measurement. This thing. Now this should depend. Hold on. What are you doing wrong?
So you can actually dial up the amount of interference. It's not like a Boolean on-off scenario. There's a way to increase or decrease the amount. Has that been done in experiments? Oh.
So basically, like, think about it like this, like, when it is like, x plus and x minus, you can see it along like, x axis. And then 0 and plus is z axis. So when you're along z axis, like, it's particle, x axis is wave. And that, phi is basically the angle between the two.
Oh.
And like, when it's z and x, you notice like, the revision that Nick made. If somebody tells you, okay, how would you rotate? Like, this is z. If you want to rotate it along like, x axis, it's going to be rotation ry. Like, you're going to rotate it like, along ry axis, which is like, why Nick added like, rotation around y axis. And if you look at the probabilities, you see like, that's the part that I mentioned. Now look at the first term and the second term. You see like, it's in a sense complementarity, because you see like there is only a plus and minus difference there. And if you add them up, like, in a sense, like, they kind of like, cancel each other if you consider all of them simultaneously. So you're plotting like, the plot, like, you said that argument, yes.
Yeah. What is it? What's complaining there?
You're saying like, that
just
evaluate. Yeah.
1113.
Yes.
So phi is no interference, but they, depending on the angle, rotations can.
That's wild.
So we're changing this angle of rotation. That's mean the our level of erasure.
Are you going past 90 degrees? Is that why it goes back to something that looks like less interference?
Yeah. It's like
maximum. Yeah.
This is.
And the only difference would be it's like a flip. So when it's maximum, it becomes minimum, and vice versa.
Very cool.
And by the way, if you think about a detector, like, those maximum is like, when it's brightest, and those minimum is kind of dark. That like, that's what you would observe in your detector.
It's like minimal probability of a photon landing in that spot. Or maximum probability.
Yeah, when it's like, the minimum, basically you don't see it, the maximum, that's the highest probability that you would see.
Actually, I was reading about that. The correct terminology is actually probability density, because at a point there's infinitely many points, so there's zero probability at any one point that a photon will appear. So apparently these things are modeling probability densities.
Yes, exactly. Yeah. So this is just a comment about this particular erasure procedure, because I didn't know how this should have been experimentally realized, but this is more clear and leads to the same result. You just measure this, but then you throw a coin or something and just discard it this way. So, but blindly. but it leads to the same kind of result. The interference reappears.
And this is the part that, it's just like, people, they have to be careful about quantum eraser. That's literally what Nick said. Like, let's say that, like, you run many experiments and you have all the data. Then you would say, now I want to do some extra cleaning of that data by looking into the other quantum system that I store the past information, which is basically here the second wire. So basically it's like you look into your data and you will say, okay, I'm going to take only this part that corresponds to this piece, and you would see the interference pattern. And then the other piece, it also shows the interference pattern. But again, if you look at all of them together, you don't see like, anything new. This is basically like, in a sense, if an observer just look at the first wire data, they don't see any effect of like, the second one. Like, this is one thing that people, they have to pay attention, that this joint probability is a new thing, but the individual one, they are still the same as before. And as you see, like, as we are trying to explain that, you would notice, like, why the terminology of, probability theory is a very good terminology, because you clarify that, like, oh, this is an event condition on this result. And it is, in a sense, like, the terminology that we have in probability theory.
Makes sense.
So what else do I have here?
Can I make a very quick? Can I ask some quick cosmetic question?
Yes.
Is there a reason why the brass and kits don't match with the triangles where they're embedded?
Yeah. Well, historical reason, right? Because usually ket is the state, right?
Sure.
But the diagrammatically usually refers to state that has something like an output, so it makes sense to draw it with with this flat face to the right. But like when you write your kets and brass on the paper, you usually compose to the left, not to the right. So that's just the difference between the usual notation, with Dirac notation, and diagram notation going to the right. That's why they don't match.
Okay.
which also annoys me, but this is
okay. I'm glad I was not alone in noticing that.
Yeah. Okay. Should we go like to the completely different way of encoding the same kind of setup?
Yes,
which
I'm interested in that.
would make like a more complicated optical setups. I think it's going to make it more clear, like the ones I showed like in the beginning, like these pictures. The annoying part of this particular setups, when you try to encode the information of the path to a single system, like a qubit, is weird, because in a way you want to encode it somehow spatially to separate those two different beams that go in an actual different directions in space somehow separately, and it makes sense to separate them as a tensor product, because that's the most natural way to separate systems in the quantum theory, right? So in a way, encoding this information about locality into a single qubit, it's very weird. But it's equivalent in a way. You can do it, but it's not very natural. So the second quantization, that's why I claim is more natural to encode these optical setups. When you actually encode information whether the photon on the right or left path as a separate element of your basis, and you have the special basis that created right here, just some code to show the idea, instead of having a basis that I had before, like two-dimensional basis showing like left or right path, right, left or right. Instead of using this basis that just encodes the information whether which path it is on this qubit, you first encode the photon basis as just whether it's present or absent, right? You just have this second quantization that encodes the occupation number, essentially, right? But you can also specify more photons because they are bosons, they can occupy the same state. Multiple photons can occupy the same state, so that you basically have more of them in the same basis. So you can create bases that contain arbitrary number of them. So you can encode the absence of photon or how many of them are in the same place. So that's the occupation basis for boson or photon in this case, right? So you just take the laser, essentially with the same kind of photon, you can truncate this Fock space, essentially the occupation number, to whatever number you need it for this particular experiment, right? You can take the binary one, whether it's present or absent, and indicate just the laser or absence or presence of the laser signal, right? Assign some color to it to make it more visible what's going on, so it actually matches the color on this original picture, right? The cyan color represents the laser, right? You represent the slits themselves as an operator that takes this particular photon and this basis, whether it's present or absent, and splits them on the either to the left or the right. And now you explicitly model the path by two systems, so that it takes 1 as an input. Now you have bra, it's your input, and cat is your output. As we just discussed, it's not, so you have to read it from right to left, and naturally to the diagram direction. So you read this notation for the operator from right to left. If you have an input presence of a photon as an input, which is the laser, then you split it either to the left. Now you indicate the left one by the red color, or to the right, right? Or if there is no laser, you just do nothing. So you just naturally just describe this operator like this, and it's an operator which in this case has 2 outputs, and it's even unitary in some sense. Technically, it's in a symmetry. I think that's the name for this, but that's an indication that it's kind of a valid map to do in quantum theory. Then you do this next piece on the picture.
Nick,
right?
like, I think if you show that, like, on laser, maybe people, they would see it, like, how a slit on laser.
Oh yeah. Let's apply this to the laser. And the output would be just a superposition instead of 2 qubits. Basically equivalent to the Bell state of sorts, one of the Bell states. But now you have 2 systems instead of 1. So instead of using superposition to encode the switch-way information, you now use the actual entanglement of whether your photon were left or right by encoding the path information.
Let's just like remind, like, the audience, like, why we call it, like, second quantization approach. We know that, this is truncated, like, Fox space, but pay attention, like, if you're in the first quantization, like the first double slit experiment that Nick showed you, like, that Hadamard was literally like, your slit. You had only one wire, right? Like, it was one system, and then you create a superposition, and that was it. Okay, so this is literally like, the effect of the slit. That's how you can see it. And then if it applies on 0, you would see, like, the superposition. When you come to, like, this second quantization language, you see here, like, there is a price that you have to pay. For example, now, even the truncated space, you need 2 systems because you have, like, like up and down or left or right. And it is important to say it's vacuum on the right and 1 photon on the left and vice versa. Like, that's why, like, you see, like, do you see it as, like, 2 system here?
Yeah. Well, I wouldn't say that it's like some price we have to pay. In a way, there's some benefit to it anyway. So we'll see that it has its own benefit. Because the next element that we have to model is the beam splitter. It's the most important actual element in the whole optical setups. It's inability to model the beam splitters. And there's some complicated setup, but you can also read how the action of a beam splitter on the state. I guess you can also show the example. Because you can read it as now it models the interference more directly. You have to, like, maybe I should draw some pictures here. It's missing some pictures. Hold on. Let's draw a beam splitter like this. And you imagine that it can take, like, some photons can arrive to this beam splitter. They can either pass through it, or they can. Actually, I should have drawn it this way. So if it can pass through the beam splitter, or it can reflect from it. And the other way around, you can also, or if it goes from this direction, right? It can similarly can pass through it or reflect from it, right? So this kind of a setup. And the input and output photons are now encoded as occupation numbers, as your brass here, the operator. So we can imagine that this one is red and this one is cyan. Maybe I should, well, I'm not going to color it, but then you can model whether they interfere or not by this, if they pass to only a single direction or only to a single one. Like if it's the only single photon arise at the beam splitter, there's no interference and it just goes through it, right? With no interference. maybe there's some reflections going on, right? But when there are two photons coming, they can interfere with each other, and the photon only goes to a single direction. That's how you should read it. It's a little bit complicated. There's also some phase involved. But that's the physical interpretation of the beam split. You can even see that it's also unitary. That's how you can confirm that it makes sense.
Just
Okay.
to be picky here, like, Nick, put the reflection on the output. So like, it's more clear that, so you did kind of do the reflection to the right. So like, the input and the output, like, is more clear now.
Oh, you mean like from here?
The arrows that
Yes.
are bouncing should be arrows that are up on the
All
right.
of them, yeah. Yes. It's just like, for the sake of consistency of.
Can I do it like this? I'm gonna just cheat.
You have to split the.
Yes. Okay. Oh, now like, the direction of arrows are like, even I think like, people, they get it. Like, we know that input output, like, just the output, those two arrows, put it to the right side of like, beam splitter, like, Nick did here. Okay.
Got it.
Yeah, let's see the example. Again, applying the beam splitter to this superposition that we already created. Right, and now it makes, again, a superposition, but now there is, again, either a photon present or absent. Only a single present and one of the paths. There is never like two photons coming through. It's just for completeness sake. We will model the beam splitter in this way. Right? And some phase, global phase, I guess, is also introduced, but we can ignore it. But anyway, like the whole setup now looks essentially like this. Right? Now you can show the circuit together with the laser as a single source of photons, the beam split, the slits actually creating now occupy like two systems, so you can actually show the path with the wire in the diagram, so it makes more natural. There's some phase applied to one of them to now again to parameterize the direction of the screen, right? And then this beam splitter, I show it like this, kind of makes sense also diagrammatically, but you have some freedom in actually how to draw it. The beam splitter is the data operator that we created, and then you would just put the detector on those like here and here essentially, or here and here, because if this is the input, this is the output. You have two detectors here, and you detect both of those paths directly, right? And essentially what you get is a kind of an interference again, but it's going to be a slightly different form if you like. I don't even have like an explanation why it now has this different formula depending on the angle, but a simple explanation where it's coming from is just computationally that's what you get. Before we get, you remember we had some cosine theta squared, right, for the form of the interference pattern, but now we get this instead, whether your detector fires or not depending on the angle. If you just look at the one of them, right, it's like we averaging them out instead. It's like if you do this times this, like this is the right detector fires, this is the left detector fires depending on the angle. I think that's going to be basically proportional, right? So this is like, I don't know, this is some kind of averaging between them. You can extract the previous picture. Yep. Or rather, it's I don't know. Technically, maybe because if those are probabilities, it doesn't make sense to multiply them because they're dual to each other. Maybe. Well, I don't know how how those particular two Mats, do you know why is this particular formula we get for the interference pattern? Is it correct?
Let's see, like, you did the angle and what's going to happen, like, if you just, put the angle half of that, like, is it going to, I'm just wondering if it's just a factor. Yeah, and let's look at the and then, you know,
And naturally here.
or the other way, like, you know, maybe 2 times more, and then full simplify that.
Well, it's still, well, just gonna turn into, like, you mean this expression itself?
Mm-hmm.
I don't think it's gonna combine it with anything else. It's not gonna be.
Okay, so it's not that angle.
Well,
It's the same shape, right? It's just, is it a different formula that's representing similar shape?
for our sake, we just care about whether there is an interference or not. Not in particular what shape it is. Right. Maybe this one is because it models more directly the optical setup. Maybe this one is more right, but we need to actually check.
Maybe we discovered a new paradox.
I don't know. You can look up the formula for the double slit experiment, but the actual formula is for the geometric setup with the screen, and when you apply the optics there, what's the formula there?
Okay.
We should look it up. All right.
Aha. Okay. Now we get paradoxical. Maybe.
No, not yet. We're just gonna you generalize the circuit above, and gonna complicate it much further. Because now after the slits, we're gonna split it. We're gonna introduce that crystal. The
PBS
right,
crystal.
also.
Nick,
Yeah.
can you show, like, you know, the picture on the top next to this circuit, like, you know, so people, they would see the actual optical shape setup and this circuit. Yeah.
Yeah, I think this one is now corresponds to this one. More or less directly. Okay.
BBO crystal, that's what it's called.
Yeah. So now it's like you can see both all the components, laser, the slits here, you have paths modeled by multiple systems. When there is splitting with the crystals happening by this Glantops and prism, by the prism essentially, you see that there's also multiple paths created. Actually, let's see what's the prism is doing. You also introduce the similar kind of basis for the occupation number, but now you can have like 3 states that the photon can be in, or the path, I guess, in the setup can be in. There is the photon either absent, or it can be polarized vertically or horizontally. So you model it by not a qubit, by this qubit system, 3-dimensional system, very convenient, that we can like model this arbitrary dimensional Hilbert spaces, so that we can model it directly like this. Right, so that's what polarization and prism doing. They just takes the photon coming through it. It's either present or absent, and it just creates the superposition, entangles 2 photons of like horizontal and vertical direction, right? And they go into different direction because they actually model it by different, right? So the 2 systems, and they correlated with each other because we created an entanglement between them. And after the prism photon travels, there are 2 beams going on, right? One is polarized vertically, another is opposite orientation. So they always correlated, either that or another. It's either this horizontal, this vertical, or this horizontal and this vertical, right? So, and you do the same kind of thing here on when the photon goes through the other slit, you apply some phase difference to model different orientation, different position on the screen. You apply the beam splitter to only one of the paths from after the prism, right? Like this, you apply to one cyan and one red, and another entangled part of the entangled pair goes directly to some other detectors. So that's the setup. You again want to observe some interference at this D0 detector after the beam splitter, and you also detect the actual information about the path. This way, you basically now can infer the which way information using these detectors, because you know that there's an entanglement and they correlate it. When you observe when the detector D1 clicks, you know that it traveled through this path, essentially, right? If you D2, you know that it travels through the other path. And now you
Now,
can
just to clarify one thing, like, in the optical setup, as people see, like, there's only one D0 detector. What we are doing is basically like, we are doing that in a discrete space. Okay. So basically in the real optic, like, they sweep like, D0 and they observe like, the interference pattern as the position of like, that when those two beams, like, they meet each other. In a discrete space, like, it's those two detectors that Nick called them D01 and D02. So like, that's the discrete version of that continuous detector.
Yeah.
Is there a way to merge wires in this framework? Is that even a thing that makes sense to do?
Sometimes it is, yes. It does make sense to merge them. We can even potentially merge them here in order to get rid of one of the detectors, and just to look at the one of them. It's still gonna replicate all the interference and absence of it anyway.
Okay.
Nick, for clarity, can you also show like, now I'm forgetting like, for the connectors, can you show the connectors so people like, in the diagram?
Show connect.
So it's connectors true, I guess, like, was it this one?
Oh, you see them here.
So do we see it on the beam splitter? Like, just to clarify, beam splitter is acting. Oh yeah, that we don't see it on that one. So just to be clear, like, D1, like that wire, it goes through beam splitter. Like, it's not interacting with beam splitter. That's what I was trying to say.
This wire goes directly through it.
Yes. Yeah. That's just.
Yeah. You could have like diagrammatically just showed it like somewhere on the side.
On the top. Yeah. Or at the bottom.
Yeah, just route it for here or something to make it clear.
Got it.
But yeah, it's a string diagram. You can manipulate those wires how we want. Because it makes sense. You can bend them, you can split them. All of those operations have some meaning.
One other, maybe it helps, like, people who are familiar with these non-linear crystals, like, when you pump a laser, it creates like, the entanglement that Nick mentioned. This is basically those spiders, like, Nick, if you just, hover your mouse over those spiders, that's basically the non-linear, yes, those two that, we call them Z spider. That's the non-linear effect of the crystal, creating the entangled states.
Yeah. Actually, I'm not even sure that it's a real spider. I just rendered it this way, but it actually, where did I create it? Yeah, it's supposed to model the prism. I just assigned the label Z spider so that it's gonna it's gonna be rendered as a spider, but maybe it's not really a spider. It's what we mean by spider anyway.
Good point.
It's just like this particular form. It has this operator, but maybe if you do the spider with the same one input, so it has to be a spider with 2 dimension as an input, right? And free, right? Something like this. Yeah. So just essentially spider should look like this. So if how you interpret it, it's a little bit different, especially like this is switched, right?
Okay, like then I would say, spider is what people usually call, type 1 of those crystals, because type 1 of those crystals, they do not entangle the polarization. Here we have the entanglement of polarization. That's the extra effect. That's why it is not the usual spider. Good point.
And also some coefficient difference in order to make it properly unitary.
Oh, yeah.
Yeah. But anyway, so now we have this nice diagram. You can again evaluate all of it now, the output like has this all 4 detectors. You can see what would be the probability of clicking of. Oh, there's always like only 2 detectors click at one single time, right? Any other probability is 0, and those probabilities where only 2 detectors click depend on theta in some special way. You can even compute what would happen. Like you can marginalize all of those if you want. Like I think here I just specifically select 3 and 4. Those are my second 2 detectors, D1 and D2. I just, okay, I'm gonna post select only when the D3 is gonna click, right? That's basically means I'm gonna detect the path information, right? So I'm gonna know which way information by constraining that I want this one to click specifically. And then my interference disappears. Now G0 clicks randomly with half 50% probability, right? Depending whether it doesn't matter which one I post select on, either D3 or D4. D1, right? I call them D1. Either D1 or D2, right? So the interference disappears. But it's when I just select, now I'm selecting this one, and now there's some dependence on the angle again, on the phase, and that's the again some different relation. So like all of those different interference patterns is another interesting topic, I guess, to discuss. Why there are different ways, different patterns depending on how you model it, and what's but you get something different. But that besides the point. Now we can, I guess, go to the most complicated circuit in this notebook, and we complicate it a little bit more.
Mm-hmm.
All right. I guess I even have like just as a preview. This is like a final setup for all this delay choice quantum eraser setups. There's like 4 beam splitters. There are 6 detectors. It looks like a mess.
Wouldn't it have been simpler just to the same way that you erased the data at the top, instead of had the beam splitters kind of like rejoin in the way that they erased the information, to just erase the information directly? Or were you trying to recreate the experimental setup directly?
Yeah, I was trying to do that. So you just when you see it, it's very unclear how you actually can model and compute all the properties.
True.
When you don't have a way to compute properties of the setups, they always confuse people. That's all of the paradoxes, the source of all the paradoxes.
Okay.
Usually, right?
Okay.
So you're just trying to come up with some nice principles, some nice primitives, how you just put your optical diagram, make a circuit diagram, and then you just construct a bunch of tensors, and then you get the answer. Right? So it was already problematic to for me at least, to come up with, to figure out how the beam splitter works, how to do this occupation number, truncation of the Fock space and all that. But I think at the end it worked out. So like, for example, if you I watched a bunch of videos about this particular setup when you have all of these detectors present, and so that the final argument would have been is just all those detectors are there just in order to select all possible combination that experiment can end up, right? And that's like what this final picture is showing, depending what you choose your detector, which detector you choose in order to determine what interference pattern you're going to observe, right? Because in the end, you observe the same pattern on the detector 0, right? If you're just going to fire it, nothing going to change on the screen. But then, depending on this data that you collected from that screen, depending on which one of those 4 detectors clicked, you can do some data science on that clicks of detector D0 and post-select different pictures from it. You can, if you just filter out only those clicks when it was clicking together with D1, you get the interference pattern. If you post-select those clicks, when it click together with D2, you get a different one, which is like the complement of this one, right? And if you post-select on the either D3 or D4, which just correspond to exactly knowing without erasing which path the photon went through, then the interference goes away. So you have these 4 setups explicitly, depending on which detectors click.
So just go back to the top. I'm going to try to understand this from what I learned about the experiment. So D0, where are you showing the results of D0? Or there's nothing to speak about because you're only select D0 is the combination of all of these detectors at the bottom, I guess.
Well, you just pick one of the probabilities, right? First you post-select on one of those 4 detectors, right? What you can do, let me evaluate this diagram. When you just compute it, you get some state, which encodes all the probability you need, right? It's a 6-dimensional state, so it's like 6 output wires. So it encodes all the joint distribution of all the possible scenarios that can happen. Then you use this probability distribution and post-select on different things. Like here, this post-selection procedure, depending which one. For example, if you want D1, this is the thing I'm gonna post-select it. It's literally just apply this bra to this last 4 detectors, right? So that's what you do. You get this joint distribution, apply this post-selection procedure. You get just a 2-qubit state, right? And this is gonna encode all the probabilities depending on the theta for clicking, or either one of the detectors clicking. Both of them gonna produce some interference anyway. You can choose. So I do this probabilities. Please test something. Pick the first one. Maybe. And the third one again. In this case. Yeah, I think this is the picture you get. Assuming that you can simplify it further, I guess. Let's try to plot it. I think that's the picture you get here. What's the range? All right. So that's more explicitly how to get this picture. If you want to get this picture, you do just swap this one to this one and compute the probability inside. You get the different probability. Actually, it's like they are a little bit inverted versions of each other. So it's interesting that this has some kind of background, so it doesn't go all the way to 0. So there's some subtleties there, but yes.
Very interesting. For people that don't know the experiment, maybe I'll try to explain what the apparent weirdness was. let me give it a shot. Okay, so basically what happens is you have a photon that goes through a double slit, and you entangle that photon so that there's now 2 versions of the photon. The original photon, or let's say this, let's say the early photon gets detected, and what happens with where that photon lands on the board is it's either going to show an interference pattern or not. That's the early photon. Now, what happens is the entangled photon, let's say the later one, goes through a series of, maybe we're going to erase the information of which path it traveled through, or maybe we don't. So let's say 50% of the time you're going to detect which path it came through. 50% of the time you're going to erase that information. That's why there's these additional beam splitters down the line. But what's key with the way that this experiment was set up is that the erasure, or the potential erasure of that information, happens after the original early photon has already made its pattern on the board. But remember, it's not making a pattern, it's just one spot on the board. So where the criticisms of the experiment come in is saying that you're only finding interference patterns with some statistical post-selection based on where the photons, where the later photon gets detected at one of the other 4 split locations, which correlates to whether the information of which path it took was deleted or not. That's so there was this concept of retrocausality, saying that regardless of when you're going to find out the information, even if it happens at some point in the future, there's this retrocausal effect that there's going to be an interference pattern now, which was like the weirdness of the original experiment. Is that a accurate way to describe what was going on there?
Well, it is, but without any paradoxes. Right? There's no retrocausality or anything like that.
Mhm.
It's like the region on this diagram happens here, right?
Mm-hmm.
It's like even diagrammatically you can slide this like all the way to the future. It doesn't matter. It's like you always get the point to understand. I think the most important is that the interference, physical interference here, the pattern here doesn't change, right? It's just the data that is collected one time, right? You run this experiment multiple times. You collected the data from this, from all the detectors, and then depending what you do to this data, depending which one of those 4 detectors clicked, you can extract some information about this ones.
Mm-hmm.
And when you formulate it like this, there is no paradox at all, right? It's just a decomposition of data into multiple ways. You just decompose it into 4 patterns instead of 1, right? If you just add those 4 patterns together, you get just a single smudge, and that's what you actually observe on those detectors when you don't post-select on anything.
So the question here would be, why is there this correlation or post-selection that happens with the erased information pathways? Why does it appear to be this correlation? So in other words, why does there appear to be an interference pattern when it ticks at D1 or D2?
Because without this bottom setup, there is one, right? Undeniably, you can just, because it's just a double slit,
Mm-hmm.
right? And then it's just a way of combine it in a weird way, so that now there are 2 signals combined into one uniform one instead. You can think of all this whole setup on the bottom of it is just this additional complication that you add in order to obfuscate your signal. Instead of having like this clear interference or not, you add it up together, but you hide it besides some additional variables.
So you put in the statistics into a quantum position. In other words, the obfuscation of the statistics is kind of like a superposition of results. I'm not using scientific terms here. What I'm trying to say is, like, if you mix up like the stats you're trying to show, then it's kind of like saying it's showing all things at the same time. In other words, 2 superpositions that overlap each other but are opposite is going to show no interference. It's two interference patterns that are opposite. It's gonna be like a normal probability density.
Mm-hmm.
I think
you see, like, the challenge is, like, in a sense, like, a narrative challenge. Like, we have a beautiful mathematical construct that reproduce all the experimental results, and all those experimental results is basically the probability of different events. the moment that you start asking, you know, more questions, like, you know, you will end up with this strange situation. That's why, like, you know, most, you know, scientists, like, they are very conservative. Like, you know, they always tell you at best that, oh, like, let's stick with mathematics. Like, you know, this is the evolution of the, like, you know, wave function, or, like, you know, those amplitudes, and that's how it evolves, and that's it. Beyond that, like, you know, what can be done, like, you know, I think, like, you know, everybody agrees that, you know, at least quantum theory does not provide you any clear answer to those questions. Does it mean, you know, one has to go beyond quantum or else? Like, you know, I think this is an open question for the past 100 years of, like, you know, foundation of physics, and people are still exploring different possibilities. Now, talking about different narratives, like, you know, Nick, at the beginning, you mentioned, like, you know, you have some ideas of, like, you know, using the language of, you know, probability theory, how you want to explain these evolutions. How would you like to elaborate a bit on that?
Sure. Yes. Well, first of all, my favorite experiment, or paradox even, is only those that are arise from Bell inequality, right? Because this kind of all interference effects, they all can be explained, already known. I think they all can be explained classically, right? They don't have any weirdness. The actual weirdness of quantum theory comes when you have to explain some local correlations, and those correlations are not exactly classical, so they have some additional component to it. So in order to actually explain what's happening behind the math of quantum theory, you have to go to those Bell inequality setups, like that CHSH one that we have, and that they have been explored in some detail already. So this setup is actually more interesting to me, because it makes this narrative about locality and correlation between different parts of the universe make it more explicit, and how this correlation can arise, and trying to interpret that using some classical notions always encounters some problems, right? And the way my current understanding of this locality explanation, because the goal here is to come up with some nice local story, like here, for example, just to remind this what the setup is here, right? You have three parties, usual Alice, Bob, right, interacting. They are located on a different parts of the galaxy, maybe separated too far away, and there's some third party that sends some classical bits, maybe like results of some random coin toss to both parties, Alice and Bob, and then they perform some experiment that is conditioned on that Charlie's random choice of coin toss or whatever. They output some answer, then they just bring together those answers somehow in the future, compare the results, and they just get some weird distribution that you can't explain classically or construct classically, with explaining that they have some actual local interactions, right?
So the part of that story that's important there is that they also have an entangled particle, each of them.
The correlation that is weird is only happens when they share this entangled particle between them, right? If you don't share it, you can all good and nice. You can explain everything locally and probabilistically, but when they share this entangled pair, and you want to come up with a story, nice local story about what Alice and Bob measures in their corresponding laboratories, and having some certain outcomes, then you encounter some weird problems with negative probabilities and all that, right? So the way I want to explain it, I have some new pictures I just made recently. Let me find ones.
As Nick, you know, pulling up those pictures, like, you know, another way of, like, you know, talking about this experiment is with the best classical method, the chance of winning cannot go beyond 75%. So, like, you know, it's that's the cap. But if you use, like, you know, quantum correlations, you can beat that. You can go, you know, more than that.
Yeah, this whole setup is actually can be described as a game. Alice and Bob play with Charlie, so that they win, are trying to win by outputting some nice answers, so that the chance of winning is the maximum, and the only maximum chance, the maximum chance of winning only happens when they have this entangled pair, right? If they don't have it, they can't achieve this level of probability at winning this game. But anyway, it's like, okay, I was drawing this weird. So, let me just thinking of how to start explaining this thing. First of all, you can simplify this whole setup, just combining a bunch of things into much compact forms. Like you can basically contract Alice and Bob into a single gate. It doesn't have to be so complicated. It's just some operation that Alice and Bob do locally. That's the only thing you care about. Charlie also can be thought of some kind of separate. You can even imagine that Alice herself throws some coin and Bob also throws the coin. You don't have to introduce any third parties to that, right? So you can simplify this argument, but the important thing is this Bell pair, right? It's a entangled pair, very quantum. It's very state with a very high quantum properties, amount of quantum properties associated to it. But you can think of it probabilistically in the following sense, right? I guess I can just show you a bunch of functions that we have. If you have a quantum state, the Bell state, you can transform it into some special basis so that it's gonna have, instead of amplitude, some complex amplitudes or whatever. It can be thought purely probabilistically. It can be like in this basis. Yes, okay. So just its amplitude is going to contain, instead of complex numbers or negative numbers, it's just going to contain positive probabilities. So all you had to do is just to increase the dimensionality of each of the qubit. Your original qubit is two-dimensional, but it actually has, in general, has 3 degrees of freedom. So in order to think about it probabilistically, you have to increase the dimension up to 4, which is so that you have a 4-dimensional probability distribution, which also has 3 degrees of freedom, right? So essentially, by increasing number of outcomes that your qubit is described with, instead of having like spin up, spin down, you have 4 random variables that you have to describe your qubit completely, right? Purely probabilistically. Now you increase your number of dimensions to 4, and that's the full alternative representation for the qubit that you can have, right? And you can do it for more qubits, like in this case, Bell is an entanglement of 2 qubits. You can also cast to this basis, cast this representation, and also represent the whole state, this entangled state, as a joint distribution between these 2 random variables with 4 outcomes, right? So 16 in total, right? So that's what you can see here. It's like 16 total outcomes that have some probability. It's either this number, 0, I guess there's nothing else. But the point is, it's just a probabilistic joint distribution of 2 random variables, okay? In order to, then you answer this question, because you want to describe the system locally, right? From Alice's perspective, from the Bob perspective. So this joint distribution is not a good candidate for that. You want to decompose it into separate distributions so that you can just only act with whatever Alice is doing in her lab on this particular separate system, and also for the Bob. So in order to separate your joint distribution, you can write it down. You can do like some linear algebra and just actually introduce some branching directly. So that's what the branching is coming from in this picture. So branching is an essential part, but it's to make it more explicit, I say that the branching has to be done whenever the entanglement is introduced, right? So as soon as you have an entanglement, which is this non-separable state by the definition, essentially, right? If you have an entangled state, meaning it's not separate, you have to separate it or decompose it into a sum of separate pieces, right? And those are the branches. So for example, the Bell state, those are just keep this picture in mind. You have 4 separate branches, right? I'm going to explain what those actual things are in a moment. But the point is that you can separate the Bell state from the beginning into 4 separate branches, and then everything in this setup acts completely locally on those setups because in all individual branches. And because every individual branch started with some nice probability distribution, right? Then it's going to continue to be a nice probability distribution when those local experiments are going to be acted on them, on those parts. So you basically act locally, Alice operates on their part of the system, her corresponding distribution somehow modifies, right? You can model it whatever you want, stochastically or with any probabilistic formalism of sorts. But the point is that it's like any branch is just linear. It's not even a multiway system, right? And there's no branching, no more entanglement is introduced from the point of perspective of Alice and Bob. It's just a pure single way evolution happens now within each of those branches. And each of those parts are only evolved probabilistically, actually, but with some caveat, right? Because it would have been evolved probabilistically if those operations were purely classical in a sense. But what Alice actually, what happens in this picture is that sometimes locally, even locally, Alice can introduce negative probabilities. So within each branch. So all those negative probabilities disappear only when you consider all of the branches together. And that's like the most important thing that has to be explained, and I have the most trouble explaining currently, right? Because within each branch, when all of the operations of Alice and Bob were performed, you have these 4 different states. This is like this left one and right one corresponding to Alice and Bob, right? So they're completely separate because we separated them in the branches. But the probabilities they contain are actually not all of them are positive, they can be negative. Those like the red ones are the positive ones. This dot cursor, what the color this is the negative probabilities. Right? When you just collect them together and sum them over, you get a nice final joint distribution for the experiment you want to achieve. But individually within each branch, those contain negative probability, and I have no way of actually get rid of them. I think there's no way to within each branch to get rid of those negative probabilities. You have to explain them somehow.
Are the negative probabilities introduced by increasing possibilities, like increasing degrees of freedom? So where there is new ways to decrease a probability, that there has to be or there can exist negative probabilities at that point. It's like where there's a branching, only where a branching occurs, and you can take away probability from something having gone down a particular branch. That's where you can introduce negative probabilities again.
Well, in a way, you can think of it this way. Globally, across all the branches, it's consistent. You should get your probability distribution with only positive probabilities within it, right? But you within each individual branches, you have these negative probabilities that overall introduce this probabilistic interference, right? So it just instead of describing interference of waves, we just have an interference of two probabilities with 2 signs. It's like we simplified it as much as possible. It's like boiled down to the nature of the interference effect. But instead of waves, you're describing it by just probabilities having 2 signs, right? And if you can explain these 2 signs of probabilities, then you can explain all the interference. All right? And the most natural way to me is to come up with something like that is similar to antiparticles, but it's not quite. It's like there's some difference, but it's just a nice analogy. It's to prescribe, assign to each outcome, all possible outcome of any possible measurement or operation that an observer does to the system. Each outcome can also come in pairs, right? You basically prescribe to each possible outcome in the universe its dual that has some negative sign to it, some charge or whatever, right? And with basically you double the amount of outcomes, right? And that's how you can renormalize these probability distributions. You can basically take all of these distributions with negative and positive signs, reverse all the positive, renormalize it. Now you have double the amount of outcomes, but you interpret half of it negatively, right? So they have some negative effect to it.
That's another way to describe it. Yeah. So, but doubling the outcomes in a way that's you multiplying the degrees of freedom without actually changing you're multiplying it by 2 without actually changing any of the underlying probabilities or the resulting probabilities here.
Yeah, the point is you have to bring up these branches together. It's like if you're gonna think in terms of some individual observer living within this each individual branch, right? When you can't really describe its observations using negative probabilities, right?
Yeah.
You have to somehow come up with the story of this individual observer within each branch, right? In order to explain every phenomenon in quantum theory, right? So the problem here is that, okay, if mathematically there's a negative probability, you describe it that there is actually a dual event happened to this outcome, which is negative, but it's not observed, right? The observer himself doesn't know, or there's no way of knowing whether it's a negative or positive version of the outcome happened. Only the universe knows, and it tries to preserve, because, okay, let me try to formulate what's the difference between the antiparticles, right? Because it's not quite the analogy here. Antiparticles kind of have this annihilation effect when you have particle combining with the antiparticle and they annihilate and have zero. So they annihilate, so you have this additive property. They additively combine together. 1 minus 1 gives you 0. Here you have instead the combination of those signs of outcomes is multiplicative, right? Okay. So negative outcome and another negative outcome. Like for example, if Alison has a negative outcome and Bob has a negative outcome, the overall outcome is positive.
Okay,
so it's
that's
kind
important.
So it's wires, right? But whenever in the universe there's like odd number of negative outcomes, because you imagine you like partition the whole universe into the systems. In this one we just have 2, Alice and Bob, so you have odd number Alice or Bob just having a negative outcome. This branch got completely pruned. It got destroyed by the universe or whatever, and you can like describe it, and turns out that it's a valid point of view, because it's always the case, at least for this experiment. That's the only one I checked. I don't have a proof. But if you do it for CHSH one setup and you write down, compute all the probabilities, there's always a branch with every outcome that has a positive probability. So when there's like, you don't have to explain negative outcomes, never. Because it's like there's always some alternative for this outcome that has positive sign. Okay, so it doesn't contradict. So from the point of view of each of the observers locally, it still makes sense. It's like, yeah, but the universe somehow makes sure that this parity of charges, you only allow for the even number of outcome charges, outcome signs, right? Either all of them are positive in this case, either Alice and Bob are positive, or they're all both negative. So that when they combine, they both interfere in the positive direction, right? So within each branch, that's how the branches get merged together in a sense.
Interesting.
So that's kind of my currently the favorite way of explaining all the branching and all the negative probabilities within each branch, and how they can be interpreted locally in some coherent fashion.
Yeah. Very cool. Well, with the 4 observers here, I think my branch is definitely has a couple of positive and negatives that needs to still work out. But I really like this approach, and mathematically, in a way, you've actually shown that you don't have to think about quantum woo to appreciate a lot of these experiments. You can actually just open up a notebook, run the code, and go from there. So anyway, thanks so much for that, Nick. Thanks for the live stream. And yeah, we're gonna share these notebooks. Hopefully you can share it with us. And thanks, Mads, for joining us for this one. And yeah, I appreciate it. Hopefully we've deparadoxed some viewers. If not, you can write the code and do the maths. Think about stuff probabilistically, negative probabilities. It's a nice approach. Okay, all the